Okay, in this video, I'd like to start with a quick review of conditional probability and the multiplication rule, and take a look at the simple example. Uh, so, the conditional probability has been defined like this: the probability of an event B given condition A has been defined by the probability of the intersection of those two events over the given condition. By extending this condition or this definition to uh, intersection of lots of events, we're going to get what's called the multiplication. The multiplication rule computes the probability of finitely many, the intersection of finitely many events. So it goes from 1 to n. We're going to take the intersection of all of these. If you convert this into the intersection of two events, for example, A1 and A2, the probability of intersection of two events can be written as P1, P of A1, okay, the probability of first events, and the probability of second, A2, over given the first event. Okay, this is another way to write down the definition of conditional probability. By repeated application of this rule, you're going to get the probability of this intersection of n different events will be obtained by the multiplication of the first probability of A1, the probability of the first event, then the probability of A2, the second event, given A1. Okay? So far, we have the probability of intersection of those two, A1 and A2. Okay? Then you multiply another probability of A3. Okay? Then what's going to be the condition for this probability? The probability should be like this one. The condition should be A1 and A2. Okay, then we're going to have the probability of the intersection of those three events. Okay, by applying the is a identity repeatedly, we're going to get the multiplication rule with the probability of intersection of those n events will be product of these conditional probabilities. A, the final event, given by the condition is all the previous events, the intersection of AI as I goes from 1 to n minus 1. Okay, this is multiplication to compute the probability of intersection of many different events. Now let's take a look at an example to find the probability of this kind of intersection events using the multiplication rule. Say suppose we have 4 graduate students and 4 undergraduate students. And I want to divide these A students randomly into, I'm sorry, we have 12 undergraduate students. So we have all 16 students, and I'd like to divide them randomly into 4 groups, or 4 groups of size 4. So every group should have 4 students. Okay, so we're gonna split. We're gonna divide those 18, no, I should say 16 students into 4 groups. And I want to find the probability of each and every group as a graduate student. Let's find this probability. There are 2 different kind of approach. Just to count, okay, um, by assuming all possible arrangement or the permutation of 16 students are equally likely. Then you just count the number of permutation that satisfies these conditions. Okay, that's one possible approach. And another approach to solve this kind of problem is based on the multiplication rule that I mentioned before. So let me first show you a simple, straightforward solution. Uh, so let's think of 4 different groups. Group 1, 2, 3, and 4. Okay. For each group, we have 4 slots. Okay, you have 4 slots for the group 1, and you have another 4 slots for the group 2, and you have 4 slots for group 3, and similarly, you have 4 slots or seats for group 4. Then I'd like to assign a student to each slot randomly. Okay? And what could be the sample space? The sample space is the permutation of all 16 students. So the cardinality or the number of elements of the sample space is 16 factorial, right? All possible permutation of 16 different students. Among them, I'd like to count the cases that each group has a graduate student. There are various ways to compute the count the kind of cases. Here, let me first choose 4 factorial, which is a permutation. Permutation of 4 graduate students. Okay? These 4 graduate students. Then we assign the graduate students to each of these groups. Okay? And in this sample space, the location of graduate students at each slot will be counted as a different samples. Okay, so when you count the cases like this, you have to consider the position, the location of graduate students, these 4 graduate students at which of these slots. So we need to take the 4 to the power of 4. Okay, these numbers account to the choice of slots for each graduate student. Okay, so I suppose the graduate student has been labeled as 1, 2, 3, 4. Then we take the permutation of these 4. For example, the permutation looks like 3, 2, 4, and 1. Then the graduate student 3 should go first group, and the second graduate student should go to the second group. Okay. Then the position or the slots location of this graduate student should be determined among those four. Okay, for example, this is the slot for the graduate students number 3. And this is the slot for the graduate students for number 2. And number 4 should go somewhere in the group 3. And number 1 should go somewhere in group 1. After that, all the remaining cases are just a permutation of the 12 undergraduate students, right? For the empty seats or empty slots. Okay, it's gonna be 12 factorial. Okay, so the probability is this number 4 factorial and 4 to the power of 4 multiplied by 12 factorial over the number of samples in the number of total samples will be 16 factorial. Okay, so let me quickly compute some of these numbers. So 12 factorial cancel out those numbers out of 16 factorial. And then what remains is 16, 15, and 14, and 13. And here we have 4 factorial, which is 4, 3, 2, 12. Okay, 4, 3, 2. And we have 4 to the power 4, or 4 to the power 2, and another 4 to the power 2, 4 squared, will be cancelled with this, okay? And we can cancel this number 3 to get the rate 5, and this 2 we cancel to get 7. So what remains is 4 to the power of q, 4q, also to the 6, and 5, 7, and 13. Okay, this is the probability of the events like this. Every group has a different, every group has a greater in this division of students. Okay, this is the first kind of approach. And the second type of solution is based on the multiplication rule that we have discussed before. Again, these are graduate students, labeled for the graduate students. Then you want to construct the event which sort of converge to the events that we are interested in. So the first event is a simple one. We first consider only 2 of these graduate students, number 1 and number 2. These 2 graduate students are in different groups. Okay, this is an event. An event among these or 16 factorial samples. We consider cases such that the first 2 graduate students belong to different groups. And the second event, we consider one more student, students 1, 2, and number 3. These 3 students are in different groups. And A3, we consider all those 4 graduate students are in different groups. Okay? There are natural inclusion relation. A3 is a subset of A2, and A2 is a subset of A1. And we are supposed to compute the probability of A3. Okay, in this example, you want to compute the probability of A3. Then the probability of A3 can be regarded as the probability of the intersection of those 3 events. A1, intersection, and A2, intersection, and A3. Then, here, I'd like to apply the multiplication. The probability of intersection of these 3 different events can be written as the probability of A1 and probability of A2 given the previous event A1, and the probability of A3 given the previous probability A1 and A2. However, this intersection is simply A2 because we have an inclusion relation between those events. Okay, so let me compute these three different probabilities. Probability of A1. The probability of first two graduate students, A1 and A2. No, I should say 1. Graduate student 1 and number 1 and number 2. Those two graduate students should belong to different groups. Okay? How can you find the probability like that? In a random division of students, this probability is simply obtained by 12 out of 15. Right? How can you get this kind of number? Right? We first fix the slot for graduate student number 1. Then choose the slot for number 2 random. Okay. For example, say suppose the graduate student number 1 is assigned to the first slot of group 4. Okay. Then what's the probability of A1? These two students, graduate student number 1 and number 2, are in different groups. So say suppose this is the fixed location of the first graduate student. The probability of A1 can be computed by, we choose the slot for the second graduate student. Among 4 possible remaining slots, it's 15, okay, among 15 remaining slots. The available slots for the graduate student number 2 to satisfy this condition. This condition is 12, right? You cannot assign these 3 slots to satisfy the condition number 1. We only have the remaining 3 groups. Okay, so 12 empty seats are available for the graduate students number 2. All right, then what about the second condition probability? Probability of A2. When given A1, which means now we choose the slots for the second graduate student. Say suppose the second graduate student is located somewhere here. Then under this condition, A1, these two graduate students, number 1 and number 2, are located in different groups. What's the possibility of the third graduate student? Among random choice of the location of the third graduate students, the random choice for the slot for the graduate students number 3 will be now how much? 14. Okay, among 14 possible empty slots, on the available slots are 14. However, the valid slot to satisfy this condition, students number 1, 2, 3 should be located in different groups, which means those 8 slots are valid to satisfy the condition A2. So we have 8 slots for the students, graduate student number 3 out of 14 possible available slots. And similarly, we can evaluate probability of A3. with the condition A1 and A2, which means now suppose the location or the slot for the graduate student number 3 has been determined somewhere in other group. Then what's the probability of the A3 with given condition like this, A1 and A2? We now have 13 available unassigned seats or unassigned slots. Among them, the slots for graduate students number 4 to satisfy those conditions are 4. Okay? So by taking the multiplication of these numbers, we're going to get 8, and 4. And here we have 15 and 14 and 13. I think those two numbers are the same. Okay, this is the example to compute the probability based on multiplication of the conditional probability. Okay. Now let me move to the next topic, which is the total probability and the Bayes rule. In this section, we're going to discuss total probability theorem and Bayes or Bayes theorem. First, let me define the concept of partition of sample space. Say suppose A1 up to AN is a collection of events. We're going to say these collection of events are the partition of the sample space omega. This means the sample space can be obtained by the union of those events, AI, as I goes from 1 to n. And here, I going to put a dot. What does this dot in the union mean? This dot means this, okay, this is the disjoint union. Disjoint union. It means for sample space omega is partitioned. For example, A1 and A2 and A3. Okay, these are disjoint union. So there are no intersection between them. And the union of all these events should recover the entire sample space omega. In such a case, let's say the collection of events from A1 to AN is a partition of the sample space, and we're going to assume the probability of individual events are non-negative, no, positive, I should say positive. And we're going to have another event. Okay, suppose we have a partition like this. A1 and A2 and A3 is a partition of the sample space. Then here we have another event T. And this theorem is called the total probability theorem. This theorem tells us the way to evaluate the probability of this event B, okay, with respect to every one of the events in the partition, one by one. Okay, this is obtained by the summation. If I go from 1 to n for each and every element in the partition, we compute the probability of partition multiplied by the probability of event B given this event in the partition. Okay, that's the total probability theorem. Actually, the idea is very simple. The probability of B is the probability of omega intersection of B. And the omega, the total sample space, is the union or the union or disjoint union of individual events in the partition. Then you can use de Morgan's law to distribute this intersection over union to get the probability of, okay, can break this into, we can convert this into the intersection of AI and B. Okay? Then take the union as I goes from 1 to n. Since these AI are disjoint, they don't have any intersection. These sets, these collections are disjoint too. Okay, we can put in that here. This is again a disjoint union. Then the probability of disjoint union can be converted into the summation of the probability of individual events, AI or B. Okay. Finally, we apply the conditional probability. The definition of the conditional probability, the probability of AI multiplied by the probability of event B with respect to the given the previous event as a condition. Okay. So the idea is very simple. The probability of B, or in this Venn diagram, the probability of B is the relative area, the area of this region with respect to the area of total sample space. The area of this region can be obtained by the summation of area of intersection with respect to each partition. So we first compute the probability of this region, the probability of B intersection with A1, and the probability of B intersection with A2, and B intersection with A3. And summation of those three will give us the probability of event B. And this intersection of the event B and an element in the partition can be obtained by the product of these two probabilities, the probability of AI itself and the conditional probability of B. Okay, this is what's called the total probability theorem. The total probability is obtained by the summation of the probability of that event over individual elements of the partition. Okay. So let's consider an example, I guess. Again, let's roll fair coin, or I should say fair dice. It says four-sided dice. If first result if the result of the roll is less than or equal to 2, then we're going to roll the dice again. Otherwise, which means the result of the first roll is greater than 2. We're going to stop there. Now, in this rule, I want to find the probability of sum of your rolls. Okay, in this case, we're going to roll the dice twice. But in this case, you simply roll the dice only once. Anyway, the sum. Thus, we want to find the probability of sum. Total sum is greater than or equal to 4. Okay, and I want to apply the total probability theory. That means among all possible samples, I want to construct a partition of the sample space. Okay, right? Which means the sample space will be divided into disjoint unions of events. Here, I'd like to introduce the event AI. The event, uh, the first row is the result of the first row is the number I. Then the probability of PI and A1, A2, A3, A4. These are the partition of the omega, and the probability of all these AIs are the same. They all occur. Now, let's say B is the event that the total sum is greater than or equal to number 4. Then to apply the total probability theorem, we know the probability of individual partition. Okay? All we need to compute is conditional probability of this event with respect to each partition. So what's the probability of B given A1? So the first row, the result is number 1. Since it is less than or equal to 2, you're going to roll it again. Okay? Then what's the probability of total sum is greater than or equal to 4? Which means the second row. So the condition is this one. The result of the first row is simply 1. And the total sum, to get the total sum greater than or equal to 4, the second row should be either 3 or 4. Okay? So the probability is 2 out of 4, which is 1/2. And the probability of B given A2. So the result of the first row is now number 2. If that's the case, we're going to roll it again. Then the second row should be what? It's going to be either 2, 3, 4. Then the total sum is now going to be greater than or equal to 4. So it's going to be 3/4. For the other cases, what's the probability of this event with respect to A3? Okay. So the result of the first row is now number 3. Then you stop. The total sum is simply number 3. There is no chance to get the total sum greater than 4, greater than or equal to 4. So this is simply 0. And the probability of B given A4. Now, the result of first row is number 4. Then you stop. And the total sum itself is 4. So the probability is simply 1. Okay? Then the probability of this event, total sum is greater than or equal to 4, can be obtained by the total probability set like this. The summation. Here we have 4 different cases in the petition. The probability of AI multiplied by probability of the event that we are interested in given the conditions. So here in this example, all those probabilities are the same on color. And we have 4 different conditional probabilities. Okay? On half. And we Doral and Joe and okay. This is what's called the total probability theorem. And there is another important theorem or important rule that I'm going to use to compute the conditional probability. This is known as the Bayes theorem or Bayes rule. Again, the sample space has been partitioned into different events, A1 up to AN. This is the partition on the sample space, and individual events in the partition has non-zero probability. And B is another event, so probability is also non-zero. Okay, in this assumption, Bayes rule, okay, in similar configuration, the total probability theorem gives us the way to compute probability of event B in terms of the probability of partitions and the conditional probability of that event with respect to partition. But the Bayes rule or Bayes theorem gives us slightly different information. Excuse me. Here, we are interested in the probability of a partition, okay, among one of them. For example, AI. The probability of AI given another event B. Okay. This rule gives us the way to compute this type of probability. The probability of individual element of the partition given another event B. This is obtained by the probability of AI given probability of B, the probability of B given AI. Okay, this denominator is an element, one element of the of this type of this total probability theorem. And numerator is just the probability of B itself. And by total probability theorem, you can write down as a summation of probability of AI and the probability of I think it's better to use different index, AJ, J, since we are AI responds to the index here. So actually, this is very simple result of the definition of conditional probability and the total probability theorem. For example, the probability, the conditional probability of AI given B is written as the probability of, this is simply the definition of the conditional probability. The intersection of AI and B over the probability of B. Okay? And this intersection And another can be also written in this way. The probability of AI multiplied by the probability of another event, the other event, B, given AI. Okay? And the denominator, probability of B, can be converted in this way. That's the total probability theorem that you mentioned before. Okay? So the proof is very simple, very easy, but what's the importance of base function? What's the meaning of that equation and identity? So Green's rule, Bayes' theorem, is very important both to address the kind of problem known as the probabilistic inference. The inference. What's an inference? In this probabilistic model, say suppose A1 and AN, these partitions are considered as causes, and B is a fact. There are many different causes to produce this kind of events with a appropriate probability. In this kind of probability model, we have this the probabilistic inference, which is the guess. I try to guess the cause of the observed effect. Okay, that's the problem known as probabilistic inference. Okay, we observe the event B, then want to analyze which one of them is the cause of that event, that result. But here, the given probability model is something like this. The, you're going to given the probability of the effect given individual causes. So you're given the cause-effect relation. And also the probability of individual causes. With this kind of information, I want to find the probability of individual cause given the effect. So uh, basically we want to compute the probability of AI, the probability of one of the partition given the effect. Okay, this is the conditional probability of AI given the effect, and this is the probability of AI itself. Okay, we're gonna okay. So those two are essentially the probability of one cause AI. Okay, the difference is either you are given the condition B or not. Okay, this is simply called the probability of AI, and this is the conditional probability of AI given B. And there are another name to distinguish those two probabilities of cause AI. This one is called the prior probability. Okay? That's the probability of this event before we know the result. Okay. However, in prior is something related to the before something. So this is the probability of AI before we know the result B. But this is the probability of AI after we have information of the effect B. So this is also called posterior probability. Now, this is the probability before we know the effect. And this is the probability of AI after we have information B. Okay. So this base rule is just a way to compute the posterior probability out of from the cause-effect relation and the prior probability. Okay, this is the posterior probability, the probability of cause AI given the result B. And the right-hand side consists of those two kinds of probability. Okay, here probability of AI or probability of AJ is the prior probability. Okay, and this is a cause-effect relation. Okay, this is a cause-effect relation. The cause-effect relation and prior posterior probability is somewhat reverse concept. Okay, this is the probability of the effect given an individual cause, and this is the probability of individual cause given effect. Okay, so the base rule computes the posterior probability given the cause-effect relation and the prior probability. Uh, let's consider this example, the radar detection problem again. A. Event A is the event that an enemy aircraft is present, which means A component is no aircraft. And B is an alarm. And B component is no alarm. Okay? So the entire situation can be split into two cases, either the aircraft is present or not. So the union of A and A complement is a total sample space, which means A and A complement is a partition. Okay? And we are given, to apply the base rule, we should given the cause-effect relations and the prior problem. So the cause-effect the cause-effect probability will be given like this. The probability of alarm given the aircraft is present is 0.99. But the probability of false alarm, the probability of alarm given no aircraft, okay? That's the probability of the radar facility generate the alarm, although there is no aircraft present. This probability is given as 0.1. And also the probability of the aircraft, the probability of enemy aircraft comes in as 0.05. That means the probability of a complement is 0.95. Okay, those are given information. Okay. Now one day, the radar facility generates an alarm. Then, what's the probability of the enemy aircraft is actually comes in when we know the alarm generated? So we have seen the alarm. The radar facility produces an alarm. Under this condition, what's the probability of real enemy aircraft comes in? Okay, you want to know this kind of value because there is a possibility of the false alarm. Okay, to do that, uh, okay, we need to apply the Bayes theorem. Uh, so we have to compute the probability of the intersection of these over probability of B, and the intersection probability will be computed by combining the posterior probability and the cause-effect relation, which means the intersection of A and B is probability of A and the probability of B are A. Okay, so the product of those two numbers. And what's the probability of B? The probability of B should be written as using the total probability here, which means the probability of A, probability of B bar A. Okay, this is actually the probability of B in intersection with A, and plus the probability of A complement with B. Okay, so this kind of probability can be obtained by the probability of A complement multiplied by probability of B by A complement. Right? This is basic. Now you can replace those probabilities, the prior probability, and the cause-effect relation problem. So the probability of enemy aircraft present is 0.05 multiplied by the true positive alarm, which means 0.99. And this is the same number, 0.05 times 0.99 and plus. And this is the probability of no aircraft is present, 0.95 multiplied by the probability of false alarm, 0.1. And using calculator, you can easily verify this. You can compute this number, which is approximately. Okay, can you guess from this observation or these numbers? Can you guess what's the posterior probability of enemy aircraft is present? This is pretty accurate data facility. If enemy aircraft comes in, the probability of alarm is 99%. However, there's pretty good probability of false alarm. Although there's no aircraft, the radar facility may generate the alarm with a probability 0.1. That's a pretty good number. Okay? So, can you guess, how do you feel? Based on the intuition. Can you guess how big is this number? Calculator, in calculator, you can get this number is approximately 0.34. 26. So it's about 34%, 33%, one third. Isn't it too small? Yes. I feel it's too small, but that's correct number. Okay. So there is but the probability of real enemy aircraft comes in is approximately one third. Which means uh, out of three alarms, there are only one correct alarms. The other two alarms are false alarm. There is no aircraft, no enemy aircraft comes in. Although the radar facility generated the alarm. Okay. So this system is not very excuse me effective. The first guess. Okay. There is yet another example, which is even more dramatic than the previous example. Uh, Say suppose we're considering a rare disease of the probability 0.001. Okay, so the probability of a person has this disease among the population is 0.01, 0.001 to 0.1%. Okay, so roughly 1 out of 1,000 people has this disease. And there is a test method. A test method of 95% accuracy. This kind of test method is developed. And how can we compute? What's the meaning of this 95% accuracy? Which means, uh, let's consider this event. Say, suppose on event A is which is an event, a randomly chosen person has the disease. Okay, so the probability of this event is 0.001. And B is the test result. Test result is positive. Then what's this 95% accuracy means? The probability of B given A. Okay, if we're given the person, if the person has a disease, the probability of getting correct test positive result is 95, is 0.95. And what about the false result, false positive? And this 95% accuracy also means the probability of negative result given person without the disease is also 0.95. Okay, that's the meaning of 95% accuracy. That's a pretty good test method. Okay. I was to find the posterior probability. The probability of A bar B. Okay. So randomly chosen person comes in, and the test result is positive, and the accuracy of this method is 95%. So, with given positive test result, what's the result? What's the probability of this person actually has that disease? Okay, before we compute this number using the Bayes theorem, let's first guess with our intuition. So, okay, before we actually compute this number, let's guess among those those choices, what's the most approximate result, approximate value for the posterior probability? For example, or 95%. Or okay, and we could start with 99% and 95% and 90% and 50% or 10%. Most approximate. What's the most close value of this posterior probability? Actually, the result is quite surprising. Let me first consider excuse me, the probability of B given A complement, the first positive probability. Okay, the test result gives us true result, although the person does not have that disease. Okay, this is one of the cause-effect relation. Okay, this should be obtained by 1 minus the probability of B complement given A complement. And we know this value is 0.95. So this is 0.05. And by Bayes theorem, the probability of A bar, the posterior probability, is probability of A. Okay, the prior probability multiplied by probability of B bar A. And the probability of A, probability of B bar A, and plus probability of A complement and the probability of B bar A complement. Okay, which is 0.001. The prior probability of this disease multiplied by 0.55 and 0.001 and 0.95 and plus. Okay, the prior probability of the person does not have that disease. A complement is 0.999 multiplied by 0.05. How big is this number? Okay, this is approximately, excuse me. Okay, this is almost number 1. Okay, which means this term is approximately 5%. And what about this one? Okay, this is approximately number 1, which means this is approximately 0.01%. Then 0.01%. This is very small, tiny number compared to this number, 5%. Okay. If you use the calculator, this is approximately 0.0187, which is 1.87%. So the posterior probability of this test method is only this much, which is far below than 10%. It's less than 2%. Even though the test method has the 95 accuracy, and the test result is positive, the probability of this person has that disease is just less than 2%. Okay, it's a quite a surprising result against our intuition. All right, let's call it a day and then stop here.